So, we are discussing about the application of reciprocal lattice. So, today we will see the Bragg law in reciprocal lattice, what basically in different form in reciprocal lattice. So, reciprocal lattice, we have discussed this evolved construction. So, what was that? So, if you take a vector along the direction of the incident X-ray, say this is the incident X-ray. So, from any point, if you take the magnitude 1 by lambda in such a way that it ends at the one reciprocal lattice point. Okay. So, this length is basically 1 by lambda. Then if you construct a sphere with this radius, then that sphere will intersect the lattice reciprocal lattice points. Okay. So, if you draw a sphere with this if you draw a sphere, okay. So, if you draw a sphere and then it say intersect some reciprocal points at different places. So, if we add one of them with this origin, this generally we take the origin of the reciprocal lattice, because this is a lattice point. So, if we take origin of the lattice reciprocal lattice point, this one. So, if you add connect from this origin to the lattice point, which on this sphere or here on in 2 dimension the circle. So, if we add them, connect them, then this will be the perpendicular bisector of crystal plane, and this will be the direction of the refracted ray or reflected ray. Okay. So, that is the evolved construction. So, if we follow this evolved construction, so this is the direction of incident X-ray, and we have chosen this length 1 by lambda. Now, this will be the bisector, perpendicular bisector of a crystal plane, direct crystal plane, so real crystal plane. So, I think it is I have to draw slightly this. So, this angle, these two angles should be same. Okay. So, it will be bisector of a crystal plane. So, crystal plane will be right. So, I can do okay. So, let us take this is point A, this is B, this N. Okay. So, here already we have discussed about this Abel construction. So, to show the Bragg law in reciprocal lattice, I need this figure again. So, here our this is, we are telling say a vector, this is a dash vector, okay, and this is another vector say OB. So, from vectorial rule we can write that k plus OB. Now, OB is we can say this is the vector, reciprocal vector H, right, because that is the definition of reciprocal vector. So, this it is the basically bisector, normal bisector of the crystal plane, and here it is same. So, this will be OB is basically we can write H. So, this H vector, this is H vector, right. So, this plus this will be this. So, that will be equal to K dash, right. That we can write from this Abel construction. So, K here K we have taken 1 by lambda. Now, I have to tell you one additional information that in definition of reciprocal lattice axis B1, B2, B3, B1, B2, B3, right. What was the definition? So, 1 by V, then A2 cross A3, etc., right. And another relation we used, that was A m dot B n equal to 0 when m is not equal to n, and this was 1 when m equal to n, right, when m equal to n. So, here 1 we have written, but one can write 2 pi also. Generally crystallographer they use just 1, but in solid state physics we use 2 pi instead of 1, but everything is valid whether you take 1 or 2 pi. So, but 2 pi physics wise one should take 2 pi, because here this k equal to 1 by lambda, but it will be momentum vector. It will be momentum vector if I write here instead of 1, or wave vector. Okay. So, then wave vector is 2 pi by lambda. So, then this k we can treat as a wave vector, momentum vector, reciprocal vector. So, that is why it is so if we use 2 pi, so then this k will be its wave vector, and in general this wave vector, this in physics we use 2 pi by lambda. So, here we will use 2 pi. When you will use 2 pi here, so this definition just we have to include 2 pi. So, here other whatever. Okay. So, generally also people use 2 pi whenever necessary, otherwise just 1 by lambda, or in this case one can proceed, but wherever necessary to include 2 pi, so one can include 2 pi. Okay. So, it is so this k is basically wave vector, and it is defined by this. So, here instead of 1 pi one can consider 2 pi, or you can take 1 pi 1 by lambda, but in sometimes when you are writing equation etc., there you can include just 2 pi. So, that way also we can deal. So, this equation is basically for reciprocal lattice, right. So, here k equal to 2 pi by lambda, and it has direction. So, if I write magnitude wise, so this is the 2 pi by lambda, and magnitude of k dash also same, right, 2 pi by lambda, but direction are different, So, they are difference in direction having same magnitude. So, here I can write k minus k dash equal to minus h. Now, whenever in this direction say h is there, so there must be another lattice point on the other direction. So, whenever plus h this direction is there, so other direction exists. So, it is equivalent minus h and plus h with direction, that is one can write. So, basically whenever your h is there, so there must be existence of minus h. So, that is why do not need to use this negative sign. Okay. So, this one can write delta k, del k equal to h. Okay. So, this is say equation 1, or the same thing is coming in other form, say equation 2. Okay. Also, if I just in other form also we can write k minus k dash equal to right. So, this basically if you take dot product of these two, so you will get square of magnitude. So, this we can write, okay. I think I will take this one. So, this so from here I can get this, and in another form from here another we can get another form. So, this basically I can write A plus H magnitude square equal to K dash magnitude square. So, this is nothing but you can take dot product. If you take dot product, so you will get, okay, let me write that will be equal to H K dash square. K dash square is nothing but magnitude, right, K square. So, I can write this K square, right. So, from here dot product you will get K square plus 2 K dot H or H dot K, these both are same, and H square. So, K square will go. So, what we will get 2 K dot H plus H square plus H square equal to equal to 0. Okay. So, we can write either this, or we can just keep the other one this other direction side. This can be minus H square. Okay. So, this is another form. So, this if it is 2, then I can say this form are basically 3. Okay. So, this is called the Bragg law in reciprocal lattice. Bragg law in reciprocal lattice. Already from this configuration I have showed that we can get the Bragg law. So, from here to Bragg law in direct lattice that I have shown you. Okay. So, this configuration we have that way we have tested the eval construction, and now we are using this construction. We got this condition in vector form. Okay. So, this form is basically it's still Bragg law in reciprocal lattice. So, either you can use 2. So, either from 2 or 3, okay. It is a Bragg condition in reciprocal lattice or Bragg law in reciprocal lattice. Bragg condition in reciprocal lattice. So, I am writing RL, reciprocal lattice. Okay. So, one can use 2d sin theta, equal to n lambda, right. 2d sin theta equal to n lambda. Also, that is for direct lattice. Also, for reciprocal lattice, one can use delta either 2 or 3 this condition for diffraction. This is nothing but it is the condition for diffraction, right. We have given this Bragg diffraction, Bragg law, that is condition for diffraction, constructive diffraction. This also condition for constructive diffraction, because this is the direction in which direction X-ray will be reflected and gives a what I should tell, this is the Bragg intensity, okay, or Bragg peak, okay, or maxima, interference maxima or diffraction maxima. So this form is very useful for different calculation, you know. So we will see this some calculation where this form will be very useful. So this so let us see this other parameter which we can calculate, and they are very useful for not only determination of crystal structure, but also the to learn about the different physical properties of solids. Okay. So let us see that reciprocal lattice and unit cell or unit cell in reciprocal lattice. Unit cell in reciprocal lattice, RL just I am writing. Okay. So just we are deriving the similar things for reciprocal lattice, whatever exists in direct lattice, crystal lattice, real lattice. So everything similar things can be defined for reciprocal lattice. So in direct lattice, reciprocal lattice, they are in different space. So that we will understand after some more discussion. So here in direct lattice, they are basically one can use coordinate, we use coordinate x, y, z coordinate, right. The space, whatever the we define the space, okay, or point in a space using coordinate x, y, z. So in reciprocal lattice also we locate the point, lattice point, reciprocal lattice point, and that reciprocal lattice point how we have identified or we locate. So that already we have discussed that is parameter HKL. Okay. So HKL parameter I have written, but it is better in reciprocal lattice. This coordinate, it is better to write n, because this HKL, this nothing but Miller indices, and as you know that in Miller indices we have removed the common factor, but in reciprocal lattice common factor has importance, because in reciprocal lattice the distance, okay, the distance is just inverse or reciprocal, right. So whatever the in half distance in direct lattice, so here it will be double, just because of the inverse of the distance or reciprocal of the distance, right. So that is why we write here this include the common factor, one can include the common factor n. Okay. So, that n basically in case of 2D synthetically n lambda. So, n was the diffraction order. So, here also its significance is similar, it's similar fact that in reciprocal lattice we are getting additional points. So, that additional points, it is not they are coming from same planes, but giving additional points. So, whatever the order in direct lattice, whatever order, and here it is giving points, reciprocal lattice point, additional reciprocal lattice point for same sets of planes, parallel planes. Okay. So, we will get many. So, it is just one point. So, n equal to 1, this n equal to 2, it will be this point, n equal to 3, it will be this point, right. So, on a line, whatever the many points we are getting, they are from each parallel planes. Okay. So, in direct lattice we have represented with HKL. So, which represent, as I told, that a set of parallel planes having same spacing, and here this is HKL point, this is 2 HKL, 2H, 2K, 2L, 3 HKL, right. So, this equivalent, it is also equivalent to diffraction order. Okay. So, that why I mentioned that one, because we will see if I get information about this point, okay, or if I consider only this point, not others, then I will not miss anything, because whatever I will get from first order Bragg-Peck, same thing I will get from the second order, third order. Okay. So, I can use one that will give me all information. I do not need basically higher order, but it appears, it is there. Okay. So, this so unit cell that we have, this simple, say let us consider simple cubic, right. So, in direct lattice we can represent this one for in case of simple lattice, simple cubic. So, A1 equal to basically AI, right. So, ijk, if I take the along the A axis A1, A2, A3, so its magnitude A I, then A2 will be Aj and A3 will be Ak, right, it will be Ak, right. Now, in reciprocal lattice, what will be the unit cell? So, I can use this B1. Okay. So, I have to find out basically B1, B2, B3. So, you can know this, take, say here I have to take 2 pi by volume, right, and A2 cross A3 means A square, J cross K, J cross K means direction will be I, and volume will be A cube, this volume will be A cube, right. So, basically 2 pi by A I. Similarly, B2 will be 2 pi by A J, B3 will be 2 pi by A K, right. So, here I am getting A B1, B2, B3, B1, B2, B3 just along the A1 direction, A2 direction, A3 direction having the same magnitude as here. So, for simple cubic in direct lattice, it is when it is simple cubic, in reciprocal lattice also it is simple cubic. So, in reciprocal lattice we are getting simple cubic. Okay. So, because why I started from direct lattice and going to the reciprocal lattice, they are connected. It is not arbitrary, right, because they are connected to this relation, that B1, B2, B3 we have defined in terms of A1, A2, A3, right. So, this is simple. Okay. And these are homework, your homework, okay, homework, just check it. In direct lattice FCC, show that FCC in direct lattice, so that is BCC in reciprocal lattice, okay, and BCC in direct lattice, it is FCC in, okay, and simple cubic as I showed here. So, this, okay. So, this I showed, and this you can just take as a homework and do it. Okay. So, unit cell, as I mentioned that siege, Wigner siege cell is a primitive cell, Wigner siege is a primitive cell. For any lattice one can find the Wigner cell. How it was found? That nearest neighbor lattice point, just take normal bisect, okay, take normal bisect, take normal bisect, okay, okay, sorry. So, one has to take half, if it is lattice point, one has to take half, not this one. This is the lattice point. Okay. So, this is the Wigner cell, this is the Wigner siege cell. So, that way primitive cell one can find out in direct lattice. So, similarly one can find out the unit cell in reciprocal lattice, okay, and that is similar, in similar way one can find out. So, in reciprocal lattice, so lattice points are there, lattice points are there, right, lattice points are there. Lattice points are there. So, in reciprocal lattice take bisectors. So, normal bisectors, see in this case normal bisector, in this case normal bisector, in this case normal bisector. Okay. So, this will be the is similar to this Wigner siege cell, okay, but it is called Bilois zone. So, Bilois zone is basically equivalent to the Wigner siege cell, Wigner siege cell in direct lattice. So, similar unit cell in reciprocal lattice, it is called Bilois zone. Okay. So, unit cell equivalent to Wigner siege cell, that is called Bilois zone in reciprocal lattice. So, in next class I will discuss about more. Okay. So, I will stop here. Thank you.